place. That's what the early French explorers called it, after the local Indian name, meaning Red River. Today, the Rouge affords passage to some of the great ore boats of the world. The huge vessels move in from the Great Lakes, past Detroit, and push on to nearby Dearborn. This is the place, and there's nothing quite like it anywhere else on Earth. Ford Motor Company's Rouge plant, an industrial city that takes in iron ore and other raw materials at one end and yields finished automobiles at the other. Our film concerns the first giant step in that process, making steel. The steel story begins on the great Mesabi Range in Minnesota. World War II exhausted much of the Mesabi's once vast supply of high-grade iron ore. But today, a new and extremely efficient process utilizes the great quantities of low-grade ore that remain. The ore, called taconite, is ground to a fine powder, and then powerful magnets draw out the particles rich in iron. Mixed with a blending agent, the particles are formed into hard pellets of precisely controlled content, producing ore of a higher grade than any raw ore the Mesabi ever yielded. In hopper cars, the pellets travel across Minnesota to the port of Duluth on the Great Lakes, where Ford ships are waiting, then on to the Rouge. At dockside, the pellets are unloaded in 17-ton bites and carried off to storage bins. Now, one of our basic ingredients is on hand. Another is coke, formed from coal in huge coke ovens. Coke is almost pure carbon, and on leaving the oven, it ignites with oxygen in the air. The ignition is short-lived, however, for a quenching tower lies just down the track. It takes nearly 10,000 gallons of water to cool a carload, and the result is a beautiful cumulus cloud of steam. Then come the blast furnaces, 3 of them at the Rouge, 10 stories high. For the first requirement of high-quality steel is pure iron, which the great furnaces provide. Elevator cars, called skips, carry iron ore, coke, and limestone to the top of the furnace. The coke will provide fuel for the furnace to melt the iron, and also will carry off oxygen from the ore. Limestone is added because it will combine with other impurities in the iron, forming a slag. As temperatures in the furnace reach 3,000 degrees, the molten iron settles to the bottom, with the slag floating on top of it. Moving in, a suspended drill bites into a plug near the bottom of the furnace. As the opening is made, molten iron pours out into a slag skimmer pit, sending a shower of sparks in all directions. Slag is skimmed from the surface of the molten iron and flows through a sand-lined trough in the floor. The slag will be used to manufacture bricks, cinder blocks, and paving materials. Other troughs in the floor carry the molten iron, and its progress is carefully watched all along the way. This inferno-like scene is repeated many times a day, for each of the great blast furnaces is tapped every 4 hours. Samples are taken for laboratory analysis, part of an overall quality control program designed to provide dependability for over 15,000 parts in every automobile. The river of iron runs out into torpedo-shaped railroad cars. They are actually rolling thermos bottles with a thick lining of ceramic brick to keep the iron molten. Some of the iron will be used in the foundry for engine blocks and other parts, but most of it is earmarked for steel, along with trainloads of scrap that move into the Rouge daily. There are 2 great oxygen furnaces, each producing as much steel in 3 hours as an old open hearth furnace could in a full day. Production begins as 95 tons of scrap metal pours into the open mouth of the furnace. Then the vessel is righted. Meanwhile, a torpedo car bottle has been rotated on its axis to pour 190 tons of molten iron into a mammoth ladle. Then the ladle is carried off to the furnace. Now comes the time to really fire her up. From high overhead, a water-cooled pipe descends slowly toward the open mouth of the vessel. Pure oxygen courses through the pipe, 20,000 cubic feet of it a minute, causing the molten mix to roar and churn, and raising its temperature to 3,500 degrees. The oxygen combines with carbon and other elements in the iron, and the whole exhaust of the vessel passes through a multi-million-dollar electrostatic precipitator that removes dust from the furnace gases. As carbon and other impurities are removed from the iron, it gradually becomes steel. For steel is basically a highly refined iron. Behind a shield, workers move in as the flaming cauldron tips slowly toward them. A port in the shield provides access to the blinding glare of the furnace. Through it, a sample is withdrawn. The exact chemical composition is critical now. Samples are quickly dispatched to a laboratory, where in 2 minutes, a vacuum spectrometer analyzes the elements present with extreme accuracy. Temperature is critical too, and a measuring device is plunged directly into the molten steel. Once the temperature is recorded, the instrument, a thermocouple, is expendable. The readings are right. The metal is ready. 250 tons of molten steel pour out of the furnace, produced in less than 1 hour. It is enough for 400 automobiles. In the control room, called the melter's pulpit, the whole operation is carefully monitored. At this stage, precise amounts of other elements may be added to the molten metal to give the exact alloy of steel desired. Then the ladle moves to the teeming area, named after an Old English word that means pouring. From a nozzle in the bottom of the ladle, molten steel pours into ingot molds, which hold up to 16 tons of the metal. Steel workers carefully guide the giant ladle along, down the row of waiting molds. The ingots are allowed to cool in the molds long enough for a solid shell of steel to form around the still molten center. After the molds are removed, the ingots, still extremely hot, are lowered into a gas-fired soaking pit. Here, after soaking up heat for several hours, they will be white hot again, at a uniform temperature of about 2,400 degrees, inside and out, just right for rolling. Lifted from the soaking pit, a 16-ton ingot heads for the first big rolling mill. Guided by remote control, the ingot moves back and forth between the big rolls. It grows flatter and longer, and occasionally is flipped like a pancake to ensure uniform rolling. Big as this mill is, it takes a fine touch to juggle a hot ingot deftly, particularly when two operators must coordinate their movements. It takes a good man 2 full years to learn this job, and 3 before he's an expert, as these men are. After about 20 passes, the steel slab, now about 5 inches thick and 35 feet long, moves on toward the scarfing machine. Here, intensely hot jets of natural gas and oxygen burn off the outer layer of the slab, removing surface imperfections. With 2 million pounds of thrust behind the blade, steel can be cut like bacon, providing 16-foot lengths that are then reheated for the next mill. The hot strip mill, stretching more than 1,000 feet from furnaces to coilers, now takes over. Here, the 16-foot slab passes through a series of rolls, growing longer and thinner as it moves along. High-pressure jets of water remove surface scale and prepare the steel for the next stage, the rolls of the finishing stands. Here, the temperature and thickness of the strip are controlled to extremely precise tolerances. Emerging at the end of the mill, the strip is cooled and then it is coiled. The result, something that finally begins to look like sheet steel. The original 16-foot slab is now over 600 feet long and about 1/10 of an inch thick. The whole process, from slab to coil, took less than 2 minutes. Joined together and cleaned, the coils are now ready for cold rolling to the required gauge for automobile bodies and panels. To provide precision results, monitoring and control equipment automatically adjusts roll openings, speed, and tension in one of the most modern high-speed tandem mills in industry. After annealing and temper rolling, the final product is a 5-foot wide coil of steel, nearly a mile long. Enough for the body panels, hood coverings, and wheel housings of 100 automobiles. Some is used for cars produced at the Rouge, but most is shipped to other Ford plants around the country as coils of sheet steel or stamped and fabricated parts. Steel on the Rouge, each coil of it reflected in every trainload of 100 cars that makes its way slowly out along the riverbank, formed and forged, rolled and drawn, checked and monitored all along the way. This attention to precision and detail by the engineers and the steel workers, the production people and the quality control people has a dramatic payoff in dependable and safe transportation on the highway.